Hello, my name is Ethan Gibbons, and I'll be presenting on explicit and implicit finite difference methods in heat transfer practice. This is for ME 4150 for Professor Dr. Shafahi. So in this presentation, I'll be next giving you a brief summary of the project. I'll be then going into the practicality of transient conduction, followed by the introduction to the equations used in this assignment. Then I will go over my data findings, conclusion, and references. So the summary of the project, we have two problems to solve. Problem A, we need to use explicit implicit difference methods to solve for the profile temperature, as the same for problem B. On the left, we have a boundary condition of a constant temperature. On the right, we are insulated. We have a set length. We are analyzing this copper rod at a initial temperature of 25 degrees Celsius, and we will be doing profiles of temperatures at set times of 20, 60, 100, and 600 seconds. Now for profile B, we just have different boundary conditions. On the left, we have a convective boundary, and on the right, we have a constant heat flux. And we will be still doing the same analysis of the profile of temperature at the same times using explicit and implicit difference methods. Now, the practicality of transient conduction in today's society is very important. It is key in analyzing overall efficiency of multi-layer building materials in 3D space. We can use it for very complex non-steady state real world situations through the help of computers and computer analysis. It's critical for environmental analysis in areas such as landfills, and it has other environmental impacts by allowing us to analyze and use the implementation of geothermal renewable resource systems, and it is crucial for engineering analysis of additive materials. Now, the introduction to the equations used. We first use the one-dimensional Fourier's law of heat conduction, and from that we can manipulate that equation to get the explicit finite difference method, which uses past known solvents to get future variables and to solve for those, while the implicit finite difference method uses concurrent values to solve for itself. Problem A, we get the temperature profile of the explicit method and implicit method. Everything is the same except for the 600-second mark, where in the explicit method, it is very linear, and in the implicit method, at the very end of the length at 50 centimeters, we get a non-25 degree profile. Now, this is interesting, and through quick analysis, one can see the implicit method here is more reliable for long-term analysis. Now for problem B, we get a little bit more clustered results. We have our explicit implicit method. They both are accustomed to a y asymptote, and they both have similar shapes, yet they both intersect the y-axis at different locations. This is probably due to my poor boundary conditions set in the system at hand. Now, for a conclusion, this presentation overall expresses the usefulness of implicit and explicit finite difference methods. We saw two real-world examples that use these systems, and it is a critical and now analytical tool of heat transfer. And here are my references. Thank you for your time, and I hope you have a great day.